Hey guys, I hope everybody's staying safe and warm. And because it's a block day, we're doing a lesson. Ta-da! So we're going to talk about inverse trig integrals. Okay, last semester when we were looking at derivatives of inverse trigonometric functions, we looked at right triangle relationships. Because if y equals the arcsine of x, then that means that the sine of y equals x. And we did some stuff with right triangles and the Pythagorean theorem, and we got these three derivatives that you see on the left hand of the screen from the Pythagorean theorem and those inverse relationships. So you're going to need to relearn these, assuming you've forgotten them, because you're going to have to be able to recognize these three forms in order to be able to work with these antiderivatives, because now, of course, we're going backwards. So if you have the integral of 1 over root 1 minus x squared dx, then that becomes arcsine x plus a constant. Same thing for the other two. So you're just going to have to be able to recognize these in the integrand and say, oh, okay, u sub is not going to work with these. I have to treat it as an inverse trig integral instead. So you're going to just have to know them on sight. So yep, you're going to have to relearn them. Dig back through those old TTKs and it might help you out. Normally I would write on the screen while doing these, but turns out that the pen for my Microsoft Surface has a dead battery. Yay. And apparently it takes quadruple A batteries. Apparently quadruple A batteries are a thing. So anyway, I'm just going to animate these. Okay, we're going to start with the example on the left. Remember that if the dx is on top, you can think of it as being out to the side so that you just have a 1 on the left. And then you should recognize it as being 1 over 1 plus x squared, which is the derivative of the arctangent. So that just becomes arctangent of x plus c. Easy enough. For the one on the left, there's a 4 and a dx on top. So the dx you can take over to the right side. The 4 you can take out to the left because it's just a coefficient. Then you should recognize arcsecant. And don't worry about it if the absolute value isn't already there. You can kind of take care of that by just restricting the domain in the solution. So because we had the 4 outside the integral, it gets multiplied by the antiderivative, which is the arcsecant of x plus c. And we kind of have to put that restriction that x squared has to be greater than 1, because if you look at the radical in the integrand, the root x squared minus 1, that only works if it's greater than 0. Obviously, if the thing is 0, you get a 0 in the denominator, and that's problematic. But you also can't have a negative under the radical in real number land, so x squared has to be greater than 1 for that to work. Okay, what if it's something other than 1 minus x squared, or 1 plus x squared, or x squared plus 1? Okay, so we're going to call that number a. And the rules for these are a little bit different for each one, and we're not going to go through all the trouble of why that is. If you're really interested, it's a topic called trigonometric substitution, and it is extremely time consuming. And it's something you're really not going to have time to work through the long way on the AP exam, to be perfectly honest. I used to teach it that way years ago, and I don't anymore because it's very time consuming. I really just recommend you, I hate saying this, memorize which ones go with which. Y'all know that pains me, right? I hate memorizing stuff. Okay, so if it's arcsine, and you have, let's say, 9 minus x squared instead of just 1 minus x squared. Inside your arcsine and your antiderivative, it just becomes x over the root of that number. So if it's 9 minus x squared, then it would be x over 3, for example. And we're just going with the positive root. Okay. So for arctangent, I want you to notice the difference between this and the arcsine antiderivative. It also has 1 over a in front of it, okay, right up here. doing that with the mouse. This is painful. So it's got that 1 over a in front of it. Okay, and again, I could go through and show you the mathematical reason for it, but it's time consuming. I've posted some old notes on its learning if you want to see trigonometric substitution, and if you're really curious why the 1 over a is there for arctangent and isn't there for arcsine, or you could just go with it. That's your call if you want to dive into the mathematics or not. That's entirely up to you. Moving on, arcsecant also has the 1 over a in front, just like the arctangent, and of course arcsecant has that tricky domain issue as well, just from that difference in the square root down there at the bottom. Okay, so arcsine is the weird one out here. Normally sine is the trig function that behaves most normally, but that's actually not the case with inverses because everything's backwards. That's not why, but we're just gonna go with it. Okay, so let's look at an example now where a is not 1. So with this first example here on the left, we do have a 2 on top. And as always, we can just take that over to the side. Of course, we can't do that with the 36. That would make things messy. So what we do is we set an a value, okay? And remember that the form for this that we just saw in that previous slide, hopefully you wrote it down, is a squared minus x squared under there in the radical. So that means that a squared is going to be 36, which means that a, the root of that, is just 6. So that right there enables us to jump to our antiderivative now, because now it matches the form. We've got 1 over root a squared minus x squared. So now we can just say the 2 that was already in the front times arcsine of x over 6 plus a constant. So it's simple enough. You just have to figure out what a squared is and what that makes a, and then just put that underneath x if it's an arcsine. Also put it in the denominator if it's in front of arctangent or arcsecant only. Okay, so look at the example on the right. Example on the right, we have a 1 on top, so we don't have a coefficient to worry about. So we look at the bottom. We have 16 plus x squared. And when you have this mixed in with all your other derivative and antiderivative rules, right? If you were trying to do u sub on this, it wouldn't work because the derivative of x squared is x and we don't have an x somewhere else on top. Okay, you always want to look for that first. But then if it's jumping out at you like, oh, well, this is inverse trig, I don't have an x on top. So you say, okay, well, if 16 is my a squared, then a is 4. And if I have 1 over a squared plus x squared, that's arctangent. And arctangent has a 1 over a in front of it. So it's 1/4 times arctangent x over 4 plus c. So that's your 1 over a times the function of x over a plus c. Okay, so what I want you to notice first about this example, it's very similar to the previous example, but there's an x on top. So don't assume that if you have something squared plus something squared in the denominator that it's trig sub. You should always try u sub first, and u sub actually is going to work here. So like usual, we're going to let u equal the denominator, 16 plus x squared. Because then du, take the derivative of both sides, we get 2x dx. And if you look at your integral, you have x dx. That's why this is a u sub problem instead of an inverse trig problem, because it has the derivative on top. So we just need to get rid of the 2. Oh, that's a typo. That should say 1/2 du equals x dx. That's my bad. Gonna fix it with the mouse that I can't write u. There we go. So anyway, then we're ready to substitute. So we've got 1/2 du for the x dx, and the 16 plus x in the denominator just becomes u. So it's in the denominator, so it's 1 over u. And 1 over u is our special exception to the power rule because that's the natural log. So, excuse me, natural log of the absolute value of u, and then we just replace u back. U is 16 plus x squared. And really, because x squared is always positive, this is one where you'd be okay without the absolute value bars in that natural log, because 16 plus x squared would always be a positive number. Okay, this example is tricky. So if you look at that denominator, we have 1, that's good, we don't have to worry about a, but then we have x to the 6th. And then on top we have an x squared. Well, derivative of x6 would be something x to the 5th power, and we don't have that. We have x squared. So also think about the fact that it would need to be 1 minus x squared to fit the pattern. Well, we could say it's 1 minus u squared to make it fit the pattern. Okay, so stay with me here. X to the 6th is an even power, which means if we take half that power, we've got its square root, right? The square root of x to the 6th, x to the 3rd, because x to the 3rd times x to the 3rd is x to the 6th. You add the powers, right? So just half of that, x to the 3rd. Or you can think of it as x to the 3rd squared, because then you'd multiply the powers. So if we let u represent x to the 3rd, then we're going to be able to say that the denominator is 1 minus u squared, and then that would fit our pattern for arcsine. So if we let u equal x to the 3rd, now it matches a pattern for u sub as well, because derivative of x to the 3rd is 3x squared dx. And look at that integrand, we've got x squared dx. We don't have a 3, so it's 1/3 du equals x squared dx. And we're using both u sub and inverse trig. So now we can rewrite our integral. The x squared dx becomes replaced with a 1/3 du. And x to the 6th becomes replaced with u squared. And now the integrand perfectly matches arcsine. So now it becomes 1/3 times arcsine of u plus c. And then of course we can't leave u. We go back and switch it. U equals x to the 3rd. Again, let me stress the importance of carefully writing down the fact that x to the 6th was u squared. U was just x to the 3rd. So this is why it's really important over in your sides to keep track of what u represents and what du represents, so that when you get back to the end, you can substitute the right thing. So if you had x to the 6th in there, it wouldn't work. Also, we didn't have an a value other than 1 this time, so it's just x to the 3rd inside that arcsine, because a was 1. You could think of the 1 as always being there, I guess. It's x to the 3rd over 1, but you get the idea. Okay, this time we have a sum both in the numerator and the denominator. Now, the laws of fractions say you cannot break apart a denominator, but you can break apart a numerator. And that's exactly what we're going to do here, because derivative of x squared would be 2x. And if we just had x dx in the numerator, we could do u sub. Or if we didn't have an x at all in the numerator, we could do inverse trig. But if we break apart the x plus 3, we can do both with either part. So that's exactly what we're going to do. So we take the x over x squared plus 1, and we also take the 3 over x squared plus 1. Now we have two different integrals that we're going to work with in two different ways. So like I said, the one on the left is a candidate for u sub because we have a form of the derivative on top. The one on the right, we don't have an x on top, but we do have a sum of x squared and 1. So that's going to be an easy inverse trig. That'll become an arctangent. Now, for the u sub on the left, because these are two separate integrals, I'm only substituting for u on the left-hand integral. So as always, well, almost always, I guess, we're going to let u equal that denominator x squared plus 1, because then du would just be 2x dx. Okay, and we have x dx. We don't have the 2, so we divide. Okay, so now I'm only replacing with u for the integral on the left, but all the x's have to go on that integral on the left. So the x dx becomes 1/2 du, leaving a 1 on top, and then the x squared plus 1 in the denominator becomes u. All I'm doing to the integral on the right is taking the 3 off the top outside the integral, leaving a 1 on top. So now you can plainly see it's 1 over x squared plus 1. Because it's a sum in the denominator, it doesn't matter if it's 1 plus x squared or x squared plus 1. They're both the same thing. Arctangent. Okay. Integral on the left, except in the power rule, that's natural log. So we're going to have 1/2 natural log absolute value of u. Integral on the right, 3 is on the outside. Integrand on the inside now matches arctangent just x, because a is 1. And they can share a constant because they're friends. But u is not friends with x. We can't have u in the answer. We go to our substitution, and u is a placeholder for x squared plus 1. So final answer is 1/2 times natural log x absolute value x squared plus 1. Again, kind of like before, x squared plus 1 is positive, doesn't matter. So absolute value or not, parentheses, doesn't matter. Plus 3 arctangent x plus c. Okay, last example, yay! So this one almost looks like an arcsecant. The problem is the 4, because it's attached to the x squared. We're not really equipped to deal with that. We need it to just be x squared on its own. So if we've got a 4 down there and we don't want to deal with it, we can factor it out. That's what we're going to do. We're going to factor out the 4 from, that's my cat meowing, by the way. Cat says hi. We're going to factor the 4 out from underneath the radical, which means it has to come out from the x squared and the 1. Remember, factoring is just dividing. So 1 divided by 4 is 1/4. And we can take that 4 and make it its own radical times the other radical, because root 4 is just 2. Aha, well now that's just a coefficient that we can take out of the whole thing and put that 1/2 in front. Boom. So now it matches our form. It looks weird because a squared is a fraction, but we've got x by itself in front of the radical, and then we've got x squared minus a squared. So we're going to let a squared be 1/4. Conveniently, that's a perfect square, because the square root of a squared is a to the 1/2. That's a little backwards. It feels a little backwards. Because fractions between 0 and 1 have a square root that is larger than itself. Think about it. Square root of 9 is 3. Much smaller. Square root of 1/4 is 1/2. It's bigger. We have a running joke at Georgia Tech that a lot of students are in the square root club because the square root of their GPA is higher than their GPA because it's between 0 and 1. Georgia Tech humor. Anyway. Now it matches our form, so a is 1/2. So we've got the 1/2 from the coefficient in front, but then if a is 1/2, that means that 1 over a is going to be 1 over 1/2. Flip 1/2 and it becomes a 2. So 1 over 1/2 is 2. X over 1/2 is going to be 2x. Okay. And then in the front we have 1/2 times 2. That cancels out. So we just get, from all that complicated mess, we get something really simple because calculus. So we get arcsecant of 2x plus c. And again, we've got that little fun domain restriction issue because if you look, you can either look back at the beginning or you can look at the form that we have. Let me switch colors here. But in order for that to be true, we have to have a non-negative number in the radical, something greater than 0. And so x squared has to be greater than 1/4. Otherwise, the whole thing falls apart. Okay, so that is inverse trig integrals. You just have to learn the TTKs and learn how to recognize the difference between a U sub situation and an inverse trig situation and a U sub with inverse trig situation. So always try U sub first. See if the derivative of the inside is present. And then if not, see if it matches an inverse trig scenario, one of those 3 TTKs. And then if that fails, see if you can manipulate the variable. See if you can let U represent some power of x, like x to the 6 becoming U squared. And see if that combination works. And then if not, if none of those work, it might just be the case that you can't do that antiderivative. Or you may have to just do it with a calculator, which is something we'll talk about later on once we get to more practice for the AP exam. But that's inverse trig integrals. Thanks for watching.